Imagine trying to locate a particle at one exact point, not somewhere inside a small region, not approximately there, exactly there, a small point in space. At first, this seems like the simplest possible description of an object. We might imagine a tiny object sitting quietly in an otherwise empty universe. But the moment we ask what is required to create that dot, the simplicity disappears. A perfectly localized point cannot be made from one wave. It requires a wave of many different wavelengths. Short waves, long waves, waves so short that their wavelengths approach zero. And every wavelength corresponds to a different momentum. In quantum mechanics, momentum is connected to energy, so a particle that looked like a simple point begins to reveal an enormous hidden structure. It contains a whole spectrum of possibilities. This is where the Fourier transformation enters. The Fourier transformation is often produced as the mathematical technique for analyzing sound, images, or electronic signals. But its deeper meaning is much more surprising. It tells us that same physical thing can be described in two completely different ways. A signal can be described by how it changes over time, or it can be described by the frequencies hidden inside it. A shape can be described by where it exists in space, or by the waves required to build that shape. And in quantum mechanics, a particle can be described by where it might be found, or by the range of momenta and energies contained in the state. The more precisely we define one description, the more spread out other becomes. To understand why, let's begin with something familiar: sound. Imagine a tuning fork producing a pure musical note. The vibration is regular, it rises and falls in a smooth, repeating pattern. If a note continues for a long time, its frequency is sharply defined. We can say with great precision that this sound is vibrating at one particular frequency. In the frequency domain, it appears as a narrow spike, one dominant frequency. Now, imagine shortening that note. Instead of allowing it to continue for 10 seconds, we allow it to continue for 1 second, then 1/10 of a second, then 1/100th. Eventually, the note becomes more like a clap, a sudden event. It begins, happens, and disappears almost immediately. But now something changes. A clap does not have a perfectly defined frequency. It contains a broad mixture of frequencies. The slower frequencies provide a general shape. The faster frequencies create sudden beginning and ending. The shorter the sound becomes, the more frequencies are required to describe it. It is not because our microphone is imperfect. It is not because our ears are limited. It is built into the mathematics of waves. A long, smooth pattern can be built from a relatively narrow range of frequencies. A short, sharp defined pattern requires a much wider range. This is the basic idea behind Fourier transformation. It allows us to take a complicated pattern and separate it into the simple waves that make it. The original sound has not changed. We have only changed the question. In time domain, we ask, when does the sound rise and fall? In the frequency domain, we ask, what frequencies are present inside the sound? And the answer to the second question explains the first. The same idea applies to shapes in space. Imagine a broad, gentle hill. It changes gradually. Because it has no sudden edges, we can approximate it using relatively broad and slowly changing waves. Now replace the hill with a vertical wall. That shape suddenly changes from one value to another. To reproduce that sharp boundary, we need higher and higher spatial frequencies. The sharper the edge, the more high frequency structure is required. This is why fine details in an image are associated with high spatial frequencies. Large areas of similar color correspond to low spatial frequencies. Thin lines, sharp corners, and tiny details correspond to high spatial frequencies. If we blur an image, we remove much of its high frequency information. The broad structure remains, but the sharp details disappear. If we sharpen the image, we emphasize those higher frequencies. The image is still the same image. We are simply separating its large scale structure from its fine structure. Now, take this idea to its extreme. What would be required to create perfectly sharp point? A point with no width? It changes from nothing to something over zero distance. To describe such an object, we would need infinitely fine spatial details. That means the Fourier spectrum would need to contain arbitrarily high spatial frequencies. The point would require waves with every possible wavelength, including wavelengths approaching zero. This is the first place where infinity appears. Not because the object is enormous, not because it contains an infinite amount of material. Infinity appears because we demand perfect sharpness. The more precisely we try to localize something in space, the broader range of wavelengths needed to create it. And this is the bridge from ordinary waves to quantum mechanics. In quantum mechanics, a particle is described by a wave function, and wave function is not quite like a water wave. It's not a physical substance that rises and falls in space at the same way as a wave on an ocean. Instead, it's a mathematical object that tells us the probability of finding an object in different places. A wave function can be spread over a large region. That means the particle has a range of possible positions. Or the wave function can be concentrated into a smaller region. That means the particle is more localized. But there is a price for making the wave function narrow. A narrow wave function must be built from a wider range of wavelengths. And because wavelength is connected to momentum, the particle must also contain a wider range of possible momenta. This is not an additional rule placed on the top of Fourier transformation. It is what the Fourier transformation naturally produces. The position space wave function describes how the particle is distributed through space. The momentum space wave function describes the waves that make up that distribution. These are the two views of the same quantum state. The broader wave packet can be made from the waves with similar wavelengths, so its momentum distribution is relatively narrow. A particle has a reasonably well-defined momentum, but if we squeeze the packet and make its position more precise, we need to combine the waves with increasingly different wavelengths. The momentum distribution becomes broader. The particle becomes more localized in space, but less localized in momentum. This is the physical meaning of uncertainty principle. Uncertainty is not position multiplied by uncertainty in momentum. Uncertainty in position multiplied by the uncertainty in momentum cannot be made arbitrarily small. This does not simply mean that our instruments are imperfect. It is not like trying to measure something with a ruler that has missing markings. The quantum space itself has this structure. Position and momentum are not two completely independent properties that we can define with unlimited precision. They're connected through a wave-like nature of the state. Let's make this more concrete. Imagine a smooth wave stretching across space. It has single wavelength. Because the wave is spread out, it does not tell us that particle is localized in one small region. It is more like a possibility spread out everywhere. Now combine that wave with another wave whose wavelength is slightly different. In some places, the two waves reinforce each other. In other places, they cancel out. Add a third wave, then a fourth, and then many more. With the right combination, the waves can reinforce on one another in one region while cancelling out almost everywhere else. The result is a wave packet, a concentrated distribution moving through space. The individual waves are not localized, they stretch far beyond the packet. The localization appears only when all waves are combined. This is a crucial idea. A localized quantum particle is not necessarily one tiny wave sitting inside a small box. It's a pattern created by interference of many waves. The narrower we want the pattern to be, the more different wavelengths we need. A broad packet may have a narrow momentum range. A narrow packet must have a broad momentum range. And if we try to make the packet infinitely narrow, the range of wavelengths become infinite. And this is why a perfectly localized particle is not an ordinary physical state. It is an ideal limit, mathematically useful, physically unreachable. Ideal mathematical version of this perfectly localized point is called the Dirac delta function. It is zero everywhere except one location. At that location, it becomes infinitely narrow and infinitely tall, while its total area remains finite. It is not a normal wave that we can prepare in a laboratory. It is a way of describing what happens when localization is pushed to absolute limit. The Fourier transformation of this perfect point has a remarkable property. Its momentum distribution extends across every possible wave number. There is no single preferred wavelength. There is no maximum wave number. There is no shortest wavelength. The spectrum is spread out across all scales. Now, consider energy. For non-relativistic particle, kinetic energy is relative to its momentum by E equals p square by 2m. As the momentum becomes larger, the energy grows. So, if a mathematical state includes arbitrarily high momenta, its expected energy can diverge. This sounds like a particle contains infinite energy, so we need to be careful. A real particle is not a perfect point. A real wave packet has a finite width, not zero width. A realistic wave packet may still have mathematical tail extending towards very high momenta, but the probability of those momenta can fall rapidly enough that the average energy remains finite. An infinite tail is not automatically the same thing as infinite total energy. The real problem appears when we demand perfect localization. The infinite energy is a warning that we have pushed an idealized description beyond what a physical state can actually provide. The universe is not hiding an infinite battery inside every particle. The mathematics is telling us that perfect precision has a cost. For light, the connection becomes even more direct. A photon is associated with electromagnetic wave. Its energy is related to its frequency. Higher frequency means higher energy. Radio waves have low frequencies. Visible light has higher frequencies. X-rays still higher frequencies. Gamma rays have higher frequencies again. So when we create a short pulse of light, we are not creating a wave with one perfectly defined frequencies. A short pulse requires range of frequencies. And since each frequency corresponds to different energy, a pulse has a range of possible energies. A long, continuous beam can have very narrow frequency range, but a brief flash must contain a broader spectrum. This is the same story as we saw with the clap. A short event requires many frequencies. A long-lasting event can be more frequency specific. A photon can still be one quantum of electromagnetic field while having spread of possible frequencies. It is not a tiny bullet with one hidden color. It is a quantum state with a particular spectral structure. When we measure it, we may detect one definite energy, but before that measurement, its state can contain a superposition of different frequencies. This is one reason the word particle can be misleading. A photon behaves like a particle when it interacts with a detector. It arrives as a localized event, but the state that describes its possible arrival can extend through space like wave. The particle and the wave are not two separate things. They are two different descriptions of one quantum state. The same logic appears when we think about time. Imagine a signal that lasts for a very long time. Because we can observe many cycles, we can determine its frequency very precisely. Now we shorten the signal. If it lasts only for a few cycles, its frequency becomes less sharply defined. If it lasts only for a brief moment, it requires a broad range of frequencies to describe it. This is why a short-lived quantum state can have a wider range of possible frequencies. The relationship is often expressed as delta E multiplied by delta T is greater than h bar by 2. But this equation needs to be understood carefully. The energy-time relationship is not exactly the same as position-momentum relationship. In ordinary quantum mechanics, time is usually treated as a parameter that describes how system evolves. It is not an observable represented in quite the same way as position. So this does not mean a particle contains a blurry clock. The safer interpretation is that the state which exists only for a short duration cannot have arbitrarily precise frequency and therefore cannot have arbitrarily precise energy. The shorter the event, the broader the energy spectrum required to describe it. A perfectly instantaneous event would require every possible frequency. Again, the infinity appears when we demand zero duration. Real events always take place over some interval, however short. Once the event has a finite duration, its spectrum has a finite width. This brings us back to the particle. In modern physics, a particle is not necessarily the deepest layer of reality. Quantum field theory described fields extending throughout space. There is an electromagnetic field, an electron field, quark field, and other fields associated with particles we observe. Fourier analysis allows us to describe the field in terms of its modes. Each mode has a frequency, each mode has a wavelength, each mode has a momentum and energy. From this perspective, a particle is not a tiny marble extending independently of everything else. It is an stable pattern within a field, a concentrated excitation, a recognizable event. It can be detected as a particle, but its underlying state is described using waves and probabilities. Position space tells us where the pattern is concentrated. Momentum space tells us which waves are required to create it. Neither description is the complete object by itself. They are the two perspectives of same underlying state. This does not make particles unreal. A particle can leave a track in a detector. It can transfer energy. It can collide with another particle. But beneath those visible events is a mathematical structure that cannot be described as a tiny object with perfectly definite properties. The particle is the pattern we observe. The spectrum is the structure that makes the pattern possible. We can now follow our entire chain. To create a perfectly localized point, we need infinitely fine special structure. Infinitely fine special structure requires arbitrarily high wave numbers. High wave numbers corresponds to high momenta. High momenta corresponds to high energy. So the perfectly simple particle leads us towards infinite spectrum. But the conclusion is not that nature fills every particle with infinite energy. The conclusion is that perfect localization is not compatible with a perfectly limited momentum distribution. A real particle has some spread in position. A real state has some spread in momentum. A real pulse lasts for some amount of time. And a real momentum has finite resolution. The Fourier transformation does not prove that space has a smallest possible length. It does not, by itself, complete our understanding of quantum gravity, but it gives us a warning. Whenever we push a physical idea towards absolute precision, a deeper structure appears. A point opens into a spectrum, the momentum opens into frequencies, particle opens into a wave function. And the wave function opens into fields, amplitudes, and probabilities. This is where our common sense begins to change. We are used to thinking that simple objects should have simple description, but in physics, simplicity can depend entirely on the language we choose. So let this sink in. The Fourier transform is not merely a tool for converting sound into frequencies. It reveals a hidden duality woven into reality. A shape in space is also a spectrum in momenta. A pulse in time is also a spectrum of frequencies. A localized quantum particle is also a range of possible energies. A single point can require infinitely many waves. A brief moment contains an entire spectrum, and a particle can be real without being a tiny object with perfectly defined properties. Beyond the particle, there is not emptiness. There is a structure, a vast architecture of waves, fields, and amplitudes and interferences. And somewhere inside that structure, the familiar world appears. So, next time you hear a sound, see a flash, or imagine a particle traveling through space, remember, you may be looking at one simple event, but hidden inside is an entire spectrum. Perhaps this is one of the deepest lessons of physics.